So let's start. It's last M seminar week and last M seminar lecture series of this semester. And so we are happy to have Piotr Sulkowski from the University of Warsaw. He's a physicist and he will speak about symmetric quivers, part which we understand, for 2D, 3D, and 4D theories and topological strings. And so this you probably will have to comment for mathematical audience somehow. All right, go ahead.
Okay, thank you very much for the invitation. I'm happy to be able to present. Well, some of the results I've been working on for several years now. Indeed, I am a physicist, so probably my approach to various problems is different than yours, but as the title indicates, the main topic are various incarnations or appearances of symmetric quivers in different physical setups. So this is what I will try to discuss. Oops. Sorry. Okay. So the main character for today are symmetric quivers. You must know what they are. Just quivers which have arrows that come in pairs. If there is an arrow from one node to another, then there is also an arrow in another direction. And physicists relate these quivers to so-called three-dimensional theories with some supersymmetry, which is denoted by n equal to. I don't think I have enough time to present all details of that. It would require like separate course or so on supersymmetry. I also don't quite know what you are experts in or how familiar we are with physics. So I'll try to be a bit general. Let's see. Just if you have questions, please ask, of course. But maybe for now, let it be just a slogan. When I will talking about symmetric quivers, at least in my mind, they are related to the three-dimensional theories. And then in last years, we have found various connections with various other theories that appear in different dimensions, as the title indicates. And some of them are related to other mathematical theories. So all that started with some observation, which now we refer to as Knot's-Quivers correspondence. The first paper are those two on arXiv, so I just give numbers. These are by Marko Stosic, my student Piotr Kucharski, Markus Reinecke, and myself. The first one is very short, just a few pages of general idea, and the second one is a bit longer with many more examples. And here it turns out that the symmetric quivers encode invariants of various knots, well, hence the name Knot's-Quivers correspondence. And there is some physical explanation of that, which has to do with relation to Chern-Simons theory. So I will explain that in more detail also in a few minutes. But for now, I just to sketch like the whole landscape of these different relations. So then another relation.
Hold on, may I interrupt
Yes.
you? Because all what I see is just a title page of your slide. So if you change your slide, then it
I'm
is not
changing here. Let me.
but it's not reflected on the screen, at least for me. If anyone see second slide, so then just let me know.
Oh, indeed. Now I see some warning that in principle I'm sharing, but the sharing is stopped. I don't see a way to.
Maybe you should redo it.
Yes, let me stop. Well, this technology. Well, maybe let me try. These are these numbers here that I mentioned. And well, what I said so far was about this Knot's-Quivers correspondence, which is one relation to or one place where the symmetric quivers play a role. But there is also another one, a bit similar in spirit, but still a bit different, which has to do with so-called Z-hat invariants. So I'm not sure how much you have heard of that. I will comment a bit more as well. But they have to do with invariants of free manifolds, and just in one sentence, these are some reformulations of Witten-Reshetikhin-Turayev invariants.
At least Sergey gave, I believe, mini-series, M-seminar mini-series maybe a year ago.
Yes.
So
Yeah. So he is one of the founders of this invariant. So this is what I have in mind. And it also turned out that they can be captured by this symmetric quivers. So these two relations have to do with theories in 3 dimensions. In a sense, both of these relations have to do with some incarnation of Chern-Simons theory, which is 3-dimensional QFT. However, quite recently, this year we have posted 2 papers. One is with my postdoc Daniel Bryan, and another with a few more people, Piotr Sulkowski, Saniuk Park, Piotr Kucharski, Dmitry Noszczenko, where we find some relations of the symmetric quivers to 4D and equal to theories. So all these theories that have been developed, starting with Gajotto, Murnaitsky, and so on, in parallel with the what Jan together with Maxim Koncevich have been discovering in context of wall crossing. So we realized that these symmetric quivers may provide some kind of reformulation of those wall crossing phenomena, which may also be of advantage for actual computations. Maybe you are less interested sometimes in actual computations, but this is what physicists are interested in for various reasons. So this is one other context. And then furthermore, it turns out that there is also, it had been known a bit maybe longer, that there is some relation between some observables or quantities in this class of 4-dimensional theories with characters of 2-dimensional conformal field theories or vertex operator algebras. And just taking advantage of this relation, we also get immediate link between the symmetric quivers and these characters of vertex operators algebras. So, to me, it's very surprising that the symmetric quivers appear in so many different contexts. Maybe I don't have very good complete understanding of that, but I very much believe that this is worth understanding better. And then there are other relations. I will not discuss them that much. Also, we don't have time for that. But just mention that there is some activity on physics side related to counting of so-called black hole microstates, which also have to do with this 4-dimensional theories. And then by all these links, it can be related to symmetric quivers. Or another aspect, which maybe has more to do with this 2D CFT picture, is related to so-called NAM conjecture and integrability. And furthermore, various of these constructions here can be engineered by so-called topological string theory, which provides, in a sense, more universal picture or viewpoint on some of these problems. And then some quantities or relations to symmetric quivers also appear from that viewpoint.
May I ask you a question? I mean, it's very general, almost philosophical. There are some errors on your diagram, yeah? And
Yes.
so everything points out to the center, to symmetric quivers, yeah?
Yes.
There should be, okay. And so in different theories, these symmetric quivers appear for different reasons, yeah? So there is not like you take some limit and you describe some limiting story with combinatorial data and they are quivers.
Well, in a sense, a bit yes and a bit no. I mean, they appear for different reasons, but for example, we have some understanding of the relation between these 4D and 3D theories. we can engineer some system, and I will mention that hopefully also tomorrow, if not today. We can engineer some four-dimensional system such that its boundary has to do with 3D theory, and then we can translate those four-dimensional appearance of symmetric quivers to 3 dimensions.
Yeah, and in some of the boxes on your diagram, I see n equal 2, no n equal 4. Yeah, it's complete.
Yes.
Okay.
Yes. So
And
that's
Chern-Simons, it's also a priori, it's probably the theory which mathematicians understand better than the other. So no supersymmetry at all.
yes. For Chern-Simons,
Okay.
there is no supersymmetry.
Okay. Mm-hmm.
Okay, so this is general picture, and I'll try to present it, well, probably also a bit schematically, but let me proceed. I will discuss various of these arrows in some order. So, general question, why are the symmetric quivers so powerful? As I say, sometimes we have more experimental evidence than probably very deep theory, but I very much hope that you might also be interested in maybe helping us understand this. So let me start with a few words about quiver representation theory. I understand that this is something you must know very well, maybe just to fix notation. So here is a picture of some specific symmetric quiver. In fact, this is not random, but it plays some role in. I will explain why it what follows, and the notation is such that D1, D2, and so on are components of dimension vector. So dimensions of some vector spaces, I just consider complex vector spaces associated to the nodes of the quiver. And in quiver representation theory, we consider moduli spaces of maps represented by arrow between these nodes, and we would like to understand some topological properties of those, specifically like Betty numbers, of course, defined appropriately. So I will not discuss all subtleties here, which you, I'm sure, know much better than myself. But let me just.
Sorry, yeah, I'm a bit confused. So omega are non-negative integers, yeah?
Yes.
Yeah,
N
okay,
is supposed to be non-negative
because in
integers.
general, omega are just integers, but not necessarily non-negative, but in this particular story, they are non-negative.
Yes.
Okay.
So these omegas are the so-called motivic Donaldson-Thomas invariants. They, like roughly speaking, are these Betty numbers of this quiver moduli spaces of for a fixed dimension vector. And there is some recipe also given by Jan and Maxim in one of the works how to find them. So the recipe is such that one should construct so-called quiver generating series, which is in the first line in this formula, and this series has some universal form. The information about quiver enters just through dependence on the Cij. We usually think of that as components of adjacency matrix of a quiver. This is symmetric because symmetric quivers are symmetric, so Cij is equal to Cji. And in addition, we also associate some generating parameters x1, d1, x1, x2, and so on to each vertex. If I can, or nodes in a quiver, if I have m nodes, then I have m of these parameters. So then the statement is that once we write this generating series in this summation form, then it can be decomposed into a product of quantum logarithm, like in the second line. So if you fix d in the second line and j, then product over k gives the structure of quantum logarithm. And then these dt invariants appear in the exponents and can be read off from such a decomposition. If one would like to find them like explicitly in some specific problem, then one can do this at least order by order and find them one by one. So much of the work we've been doing had to do with realizing that various physical observables, some quantities which are practically computed, can be written in this form of quiver generating series, like in the first line. So once we are able to rewrite something in this way, then we immediately know that one can associate this DT invariants to a given problem. And on the other hand, one might expect that there is also some, let's say, categorical level or homological level where not only these observables would match, but also some spaces behind them. So, well, the invariants are here in the exponent. What I will also hopefully manage to present is some combinatorial models which, in a sense, explain this integrality. So we find them in some specific class of examples which corresponds to specific family of quivers. It's maybe not very general, but it also suggests to us that there should be such models, maybe more generally. And well, again, probably I will not answer this question that much, what all this means on like this categorified level, but I think it's good to have that question in mind. As also some kind of interlude, I can mention that this type of sums, which here are associated to quivers, have appeared in physics literature in a bit different context some time ago, even already in the 90s, where it was realized that some characters of vertex operator algebras also take that form with some specific choice of x's. So in that case, these are not generating series, these are just some specific formulas, but exactly of that form where there is q raised to some quadratic power and possibly linear power. And also in some work of Nam, Werner Nam, such sums appeared, so they are also referred to as Nam sums, and then they have to do with conformal field theories and their deformations, which give more general integrable theories. And also there is some class of conformal field theories which are called logarithmic, for which characters have been found also to have this form. So all that in some way turns out to be related also to this quiver series. I hope to mention that in what follows as well. So to start with, let me say a few more words about this relation to knots, which started from these two papers, and then we've been looking at that in past several years. So this is again the slide I had before, which tells you what is this quiver generating series, and all that story started with the observation that quite similar structure appears in the context of knot theory and in the papers or like some line of papers started by Oguri and Vafa, which postulated, they formulated some brain construction in string theory. I will review that also in a few moments, such that the outcome was, or the statement was that if one takes a generating series of colored Comfrey polynomials associated to certain knot, so I'm not sure if you see this mouse or hand, which I'm moving. Can you see that?
Yeah.
Or not? Okay. So this P, R, A, Q, these are colored, what I denote colored Comfrey polynomials. A and Q are two variables of these polynomials. R denotes a color. So in fact, in this setting, I am considering colors which correspond to Young diagrams made of just one row, but of arbitrary length, which is R. And then the statement, first by Oguri and Vafa, and later also Labastide and Marino were very much involved in that work. The statement is that if you take this type of generating series of these colored invariants, then you can write it also in the form of product of quantum dilogarithms. And then these dilogarithms in their story appear also with certain exponents, which in that context are called LMOV invariants, which stands for La Bastida Marinho Oguri Wafa. And as you see, this form of this LMOV product looks very much similar to this product which gives motivic DT invariants, which very much suggests that if this is so, then there should be some counterpart of this first line, like a quiver series, which should also encode colored Humphrey polynomials. And this indeed turns out to be correct, at least in some very large family of examples. We don't have general proof of this statement, so this is also one of the goals, and it seems not obvious task. But the statement is such that now in a bit more detail, if we choose proper identification of these generating parameters, I go back once more. So there is obvious similarity between these two product expressions. But the crucial difference is that in the Oguri-Wafa story, there is just one generating parameter x, which has to do with some modulus of some brane in the construction that they have. And in the quiver, we have as many generating parameters as nodes in a quiver. But then, if one specializes this generating parameters xi as follows, like in this slide, so which xi is x times some power of this variables a, q, and possibly a sign, then this generating series of colored Humphrey polynomials can be written in this quiver form just with this now single x which appears here.
So this, excuse me, this kind of similarity, let's say, of two generating function, is it just sort of, is it now understood how to
well, as I say, yeah, we understand it and know how to construct it for some specific families. So, for example, for rational nodes, which are specific, they correspond just to some rational number. Then we have a construction of corresponding quiver. We don't have general proof of that for all nodes, but I will mention for which families of nodes we know that. But we know that for very different families.
Yeah, but I also mean not just construction of the quiver, but the fact that generating function of Humphrey polynomial can be expressed as DT invariant. What's the reason for that?
So we don't have very nice reason, but one hint which is quite strong is
okay, so
to so-called Humphrey homology of a given node. So this is also very surprising because the construction we start with has to do just with these colored polynomials. So in principle, we don't see any homology, but it turns out that this quivers has nodes in one-to-one correspondence with this homological generators, and also these parameters like AI here in this or TI in this identification, they encode certain so-called homological degrees. So if there is some deep explanation, it must have to do with this Humphrey homology. So
for rational, we would say algebraic nodes, there was long ago some activity. It's Oblomkov, Schende, and maybe Rasmussen, they reinterpreted the Humphrey polynomials of algebraic nodes in terms of some, well, after our work with Diaconescu, in terms of some DT invariants for moduli spaces of sheaves on on the resolved conifold.
Yes, but wasn't that for in uncolored case, or was it also for color?
For the case which you consider with just Young diagram with one row, we made a conjecture, I believe, in that paper with Emmanuel, which I believe was proven by maybe by David Schmaulik again that time ago. Somebody proved it, but I forgot who. Yeah, but again only for algebraic nodes. Yeah, when you have underlying complex geometry like complex curve, you know, Hilbert schemes, all that stuff, but not for general nodes. Yeah.
I mean, well, we have some physical, so to say, explanation why this relation should hold, but I suppose you would be interested more in some mathematical
Physics, well,
information.
but you know, Emanuel Diaconescu is a physicist, so he certainly had in mind that we do maybe, I don't know, some topological string on the resolved conifold with some maybe, I don't know,
Yeah.
open
So this
string.
I will,
Yeah,
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 also comment a bit on
yeah.
that. So that.
All right, go ahead. Sorry, yeah.
Okay. So well, so whatever said the reason for that, it has quite important consequences, and one of them is that it is clear that if we relate these two expressions I had in the previous slide, then it enables us to write LMOV invariants in terms of DT invariants. And one of the outcomes of this LMOV work, it was already 25 years ago, was a conjecture that these LMOV invariants are integer. This is so because they represent characteristics of certain states, BPS states the numbers of BPS states in physical setup. For that reason, they should be integer, but there was no proof of that statement. It was just checked to some order for some specific nodes. So one nice implication of this relation is that once we find a quiver corresponding to a given node, then we automatically have a proof that all these LMOV invariants are integer because we can easily write them in terms of this DT invariants, which are in fact proven to be integer. It was, I think, conjectured already by Jan, and then there is paper by Efimov which proves that. So that's one consequence. And what is also maybe at first sight not obvious when one considers the colored polynomials, there is in principle infinite number of them, but all of them are determined by just finite amount of data, namely this quiver matrix C and these parameters which appear here in the exponent in this identification of xi. As I mentioned, they have something to do with this homological invariance for a given node. So this finite amount of data determines by this specific form of quiver series all of these colored polynomials. And as I already mentioned, it's quite surprising that the relation to this Humphrey, or so-called Humphrey-PT homology, appears here, and generators of this homology are in one-to-one correspondence with nodes of a quiver, which also raises a question whether there is possibly some relation between moduli spaces of a given quiver, which corresponds to some node, and corresponding not homology. So just to give some examples how it works, the way we started that is we knew some explicit expressions for colored polynomials for some nodes. For example, this is the expression for colored polynomials for trefoil. So if you play a bit with this Q series, it turns out that it can be rewritten in the form of this quiver series just by using some Q identities. And then we find that quiver corresponding to trefoil not is this one which I already presented earlier. So it's adjacent symmetrics is given here. And once again, the numbers which appear on diagonal, so in this case, the 0 to 3, which represent the numbers of loops in this diagram, are these homological degrees that appear on this homological side. So in fact, yeah, I'm not defining them here properly and don't have a slide for that. If necessary, maybe I can add it tomorrow, but for now, let me just say that in words. Certainly, this is surprising that starting just from these colored polynomials, any information, even a modest one about this homology appears. So then one can play with that. I suppose this is not your main activity, but maybe you may find it interesting that we can explicitly find quivers corresponding to some knots. And in various cases, this is quite non-trivial statement to find them. So here you see that this is for some class of torus knots, 3, 4, 3, 5, and so on. These matrices are larger and larger. And this is example for 6, 2 knot. Here some negative numbers appear, in fact, but there is a way to, in a sense, avoid it by changing a framing of a knot, because a change of framing of a knot corresponds to shifting all entries of this quiver matrix by 1. So if I change framing, well, a relevant number of times, then I may get a quiver with just positive entries, and well, then I know what these numbers in this matrix mean. And this is for 463. So again, if you look at these numbers and on the diagonal and compare these homological degrees, the way when we started, it was quite surprising that we were seeing these homological numbers appearing unexpectedly. And here is some list of knots for which these quivers are known. So those which I showed, these were some examples for knots up to 6 crossings. Then for some classes of torus knots, twist knots, these are relatively simple, but also for infinite family of rational knots. And there is a class of knots which are already quite complicated called arborescent knots. That is some infinite family. This was found by Marko Stošić and Paul Wedrich. So altogether, these provide quite strong evidence that it must be, well, hopefully it is correct. But still, in general, this is a conjecture. So finding some proof of that would be very nice. And well, most optimistically, or the nicest would be to find some prescription to get this quiver from a knot diagram. But this cannot be so trivial because it is also usually not quite possible to find, or at least difficult to find this homology theories from knot diagram for more complicated homologies. And because we see some of this homological information, then it should be of at least this order of difficulty. So it doesn't seem to be a trivial thing to understand that in detail. Okay, but anyway, let me just give a few words of explanation how physicists think of that. And again, this has to do with these works of Oguri Vafa and also Gopakumar Vafa, also what Jan already mentioned, already from like quarter century ago. And it has to do with the process which is called conifold transition. This is a process where the conifold singularity is replaced either by its deformation to S3 or by resolution to CP1. And then these knots and quivers appear on two sides of this relation. Namely, knots appear as expectation value in Chern-Simons theory, which is effective description of topological strings for this left side picture. Namely, this is a setup where we have, in fact, cotangent bundle T star as free, for which we can define some version of topological string theory, and this topological string theory is described like effectively by Chern-Simons theory, and then some expectation values in Chern-Simons theory taken along closed loops in S3, which are just nodes, correspond to some observables in the string theory. So this is what happens on the left-hand side. And on the other hand, on the right-hand side, we have a dual setup where effective description is given by some supersymmetric theory in normal directions to this result conifold. And then the statement is that quantities which were encoded in topological string amplitudes in this deformed conifold, in this case are encoded in generating series or partition function of some supersymmetric theory in these normal directions, which count certain BPS states. These BPS states are represented in string theory interpretation by M2 branes, which are attached to certain M5 brane, which also encodes information about the node on this left-hand side in this deformed conifold. And then counting the numbers of those bound states encodes this amplitudes which encode not invariants. So I suppose this is a similar setup to this one in those paper by Diaconescu that you mentioned and others. So for us, one crucial information is that Oguri Vafa, when they counted those M2, M5 branes, they just had a statement that there is infinite number of them, and these numbers correspond to this LMOV invariants. And now in relation to quivers, our observation was that this infinite number of M2 branes can be understood as bound states of some finite number of M2 branes. And these different bound states correspond to all this infinite number of, we have some number of fundamental M2 branes, but bound states, there is infinite number of possible bound states which correspond to this Oguri-Vafa invariance. So again, in this schematic picture, we have this fundamental BPS states. There is finite number of them, which corresponds to the nodes of a quiver. And the arrows in a quiver encode information how bound states of these fundamental states are created. And then altogether, they give all this infinite number of this LMOV invariants. And yet, on the other hand, the same nodes of this quiver correspond to these generators of Humphrey homology. So this is like a summary of that relation. Okay, so let me also add, maybe from a slightly different perspective, but this notion will appear later on, that this quiver generating series satisfies certain difference equations, which in general are referred to as A polynomials or quantum A polynomials. The fact that they satisfy such relations follows from the statement that this generating series PC are Q-holonomic, which essentially means that they are sums of some ingredients which involve Q-Poch hammers, Q binomials, and some quadratic powers of Q.
Is it mathematically proven that
yes. So this is Garofali proves such statements, that if you have this type of series, then there must be some difference equation that satisfies.
It's equivalent, you see, existence of the Q difference equation is equivalent to the statement that some series is Q-holonomic. So then what is actually proven?
Well, by Q-holonomic, I mean that a series has specific form which may involve, I'm not writing all details, but it has specific form which may involve Q binomials, Q-Poch hammers, And
okay. So he
quadratic
proved
powers.
that certain series, actually, I spoke to him that last summer. I'm not sure that he really have a general proof, but I don't know. Maybe I forgot. Yeah, because it's like for a num, if you write a num sum, is it known whether it's Q-holonomic or not?
Well, I mean that here I'm considering the situation where I specialize at least those different x's to a single
Okay.
x, like in the Sogoly-Vafa story.
Yeah, okay,
So,
yeah. Mm-hmm. Okay.
so they should satisfy such equation. So I have here this PC of x. This is generating series. This would be so for series associated to any quiver, but specifically if I take a quiver which corresponds to some knot, then this difference equation which I have, or this a hat polynomial which gives this different equation, is the same a hat polynomial that is already known to exist from like different studies. And then this is referred to as augmentation polynomial or quantum augmentation polynomial. And also, if we take q equal 1 limit, then this difference equation reduces to, well, some symbol which I can think of as defining some algebraic curve. So this type of curves will appear also in what follows, and they can be defined also a bit more generally, not just for quivers corresponding to nodes, but if I have a quiver series and at least for some reason make the specialization to the single generating parameters, then I can define and find similar difference equation and a polynomial. So in that a bit more general context, we refer to that as quiver A polynomials. And finally, still in the context of this symmetric quivers, let me mention an important operation, some property that they have, which is the statement that this quiver series is invariant under the operation which removes a pair of arrows between two nodes. If I have two nodes in general, in arbitrary symmetric quiver, which I denote A and B, then I can make an operation which amounts to removing this pairs of arrows. So this CAB is decreased by 1. And I add one more vertex to one more node to the quiver and connect it by some pattern of arrows to other nodes. So according to this equation which I have here, because I add one more node, I also have to add one more generating parameter. So this is this XU here in the second line. And because I want to preserve the form of quiver series, then in fact, I have to specialize them in some way, like also given here. And just after this specialization, the statement is that such two quivers have the same generating series. In the simplest case, it takes the form like in this picture. So I have this quiver on the left. If I remove this pair of arrows, but add one more vertex, in this case just with one loop, and disconnected to this initial vertices, then these two generating series are equal. And this also has interpretation in terms of counting certain surfaces, like in the Gromov Witten context. So
can you comment on that, because it's something about mathematics? So first, your generating series involve DT invariants for quivers, yeah, and it's not obvious for me that they are invariant with respect to this. You say like it's obvious, then it's not obvious for me at
well,
all.
it's not obvious. So I can also give a reference. So this specific operation is introduced in paper by Pietro Longhi and Tobias Ekholm and Piotr Kucharski. It is like after our first paper, after a few months or so, it's around 2018 or so. And
yeah, but in what context? So they're dealing, so Toby consider Ekholm, he's a geometer, so I mean it's a statement about representations of quivers. So
yeah,
Volky
so
is a
yeah,
physicist,
so
so
he
how they can prove that generating series for motivic DT invariants is invariant with respect to actually changing of a quiver, because the number of vertices changes. It's dramatic. It's dramatic change. It's not like mutations or something. It's more serious operation. So how it can be proven?
well, so in the context that Ekholm is considering, these quivers encode linking uh, of boundaries of certain surfaces which are embedded in
Mm-hmm.
Calabi. So
Yes.
and so this is the interpretation that
Ah, okay. And somebody else should connect this geometry. Yeah, that's I can believe. And then somebody should connect this geometry, this counting problem to motivic DT invariants for quivers. It's
so
somebody should there should be somebody else who made that connection.
I mean, so there is this interpretation of this quiver generating series. The statement I am given, the way they prove that it's also just algebraic, so it is possible to show that in general such a relation holds for this generating series. But the interpretation is in terms of these boundaries of surfaces in Calabi-Yau. One can do some operation which is a kind of skein relation.
Yeah, that's what I meant when I said that I can believe that you can prove that some generating series of geometrically defined invariants, they are invariant. Yeah, and then you construct quivers from that geometry. This I also can believe, like vertices correspond to this, or surfaces with boundaries. But what about the correspondence between DT invariants for those quivers, which kind of, it's a difficult thing. You should choose a stability condition or something. Yeah. So it's probably, I mean, it's done by whom? Because I would like to separate something which I do not understand at all, like this counting of M2 brains. It's just words for me, and something which I can understand, like even
Yes.
counting surfaces or motivic DT invariants for quivers. Yeah, I can understand, but
I
so
mean,
then.
this interpretation in terms of just counting surfaces, as I understand, Ekholm provides that.
Yeah, that's okay. But since you say, therefore, motivic DT invariants of any quiver, you say, and so that's the last statement.
Yes. So
It's
this I'm not. I don't think this this is from this viewpoint
yeah.
explained. So indeed, that would be nice
But
to.
is it the last phrase? Is it a fact, opinion, conjecture, or what?
You mean about this?
Yeah,
Well, it is. We have a proof that.
you start with any symmetric, probably quiver. You apply operations. I don't know, either for example, this one, yeah, which
Yeah,
on the
yeah.
slide.
This one which I
Then
have here.
you end up with collection
Yeah.
of
So I
M-loop
add one more node.
quivers.
Yes.
For
I
M-loop quivers, it's easy to compute cohomological whole algebra, so you can compute DT invariants. Yeah, but why there is an invariance of DT invariance with respect to this operation? That's not clear for me.
Yes. So I mean, mathematically, I don't think I can explain that. As I say, they have this interpretation in terms of counting surfaces.
Okay, all right, yeah. Okay, go ahead, yeah.
But yeah, I'm mentioning this operation because it also, I think tomorrow, not today, but it turns out it can be also understood as reformulation of pentagon identity, which appears in the context of a wall crossing for four-dimensional theories. But this I will say more about tomorrow. And also, yet another consequence of that is that if you take some quiver, and then you may systematically remove all those pairs of arrows at the expense of introducing additional nodes. So in general, apart from some very specific situations, one can like systematically get rid of those pairs of arrows, but adding more and more vertices, one introduces, or one gets a quiver which can be interpreted as of having infinite size, but without any pairs of arrows, just with loops. So this is what we refer to as diagonalization. And in this process, this generating series is also preserved, which then means that this DT invariants of any symmetric quiver we can express in terms of some combinations of invariants just of M-loop quivers, because if you have this infinite quiver but without any arrows other than loops, then effectively this is like a collection of M-loop quivers. I mean, quivers which just have some number of loops. So this is also useful for us, at least on calculational level. I'm not sure if such a statement was known maybe in the context of these DT invariants themselves, but we also take advantage of that. Okay, so I think this is what I was planning to say about this relation to nodes, and well, just these two other comments. I probably should finish soon, right? In a few minutes.
Well, whatever, you can take up to 10 minutes if you can.
So let me just quickly say, I don't want maybe to go too much into details, but once I mentioned that, let me say a few words about this z-hat invariants, and there is a version of those called FK invariants. Here K stands for some nodes, which are in a sense a subclass of this z-hat invariants. As already I mentioned in the beginning, indeed, Sergei Gukov and also with Kumon-Vafa, Dupay, Pavel Putrov, they introduced this z-hat invariants as some way of resumming the WRT invariants, which are rational, but they conjecture that there should be some integer invariants associated to free manifolds, similarly in spirit to not invariants, which in physics picture again have interpretation of counting certain states called BPS states. And they indeed managed to introduce such kind of invariants, at least for some specific free manifolds. I mean, they have general conjecture that such invariants should exist, but some more explicit way of constructing them works for some just specific free manifolds. So, well, here is just some general formula how, in fact, this FK invariant. So, as I mentioned, FK is specific class of the z-hat invariants for not complements. So, namely, we take S3 and then tubular neighborhood of to this boundary, and then this invariants of K are in fact series into parameters Q and X. And yeah, I should also stress that this once the way they were formulated as a summation of WRT invariant means that they correspond to so-called SU2 Chern-Simons theory with SU2 gauge group. However, there is also generalization of that. This is some work I've been also involved in. There is generalization of this AK invariant to counterparts of Humphrey polynomials, where this A deformation also appears. And then we find that also in some specific examples that this FK invariance, which can be determined explicitly, can also be rewritten in this form of quiver generating series. So here are some examples of this invariance together with quivers that correspond to them. And there is also some specific identification of parameters. So this also tells us that this DT invariance associated to quivers should be encoding some interesting information about free manifolds that appear here. And furthermore, these quivers can also encode information about larger class of free manifolds, not only about not complements, but for manifolds which can be obtained as some specific surgeries along some nodes. Because also there is a statement, it was one of the papers by Sergey and others, that in case of such surgeries, the Z-hat invariants can be expressed through FK invariants for K being the node on which we do the surgery. And then the Z-hat invariants take form of a combination, certain combination of this FK invariants of this node K. So essentially in case of this surgeries, the Z-hat invariants are combination of this quiver generating series corresponding to quiver, which is dual to a node under consideration. So again, these quivers seem to encode some information about even larger class of this free manifolds. And in yet another line, it was observed that the Z-hat invariants can be identified with characters of logarithmic CFTs, which then gives us relation between these logarithmic CFTs and also those quivers. So here also the question is whether one could generalize all these observations with this generating series to the level of some homologies. The idea of this work of Sergey and others with the Z-hat invariants was that there should be some homological spaces for which these Z-hat invariants are just some like one characteristics. So the question is whether this hypothetical homological spaces could be related to quiver moduli spaces. So that's again an open question, but there is quite much evidence that these quivers also play a role here. Okay, and I'm not sure if maybe I can start tomorrow from this point, because if you have maybe a few.
Well, it's up to you. You are the speaker, you know. So do you want to stop at this point? Or?
Yeah, maybe I can stop and let's start tomorrow.
All right. Thank you very much. So one thing which I kind of, it's do not understand. I understand that there is a lot of different physics which gives rise to very specific generating series. And you mentioned that in your one of the first slide that there are some dualities or whatever between these theories. So at the physics level, so maybe you understand why this type of series appear in completely different setups. But if you are not interested in categorification, so what I see is a sort of num sums or whatever call them, this type of generating series, and why not just to study themselves without any relation to any physics, like you mentioned once that certain
Well,
series are Q holonomic, and so then there are Q difference equations which they satisfy. So it's like integer numbers appear in a very different physics, but it does not mean that all that is related to in some deep way. Why quivers? Why not just num sums and their generalizations? What specific? Only one thing which I understood that you mentioned that certain operations on quivers do not change the series, but it's operations on the generating series as well. So you just consider certain type of series like which appear, I don't know, like for example in Chern-Simons theory, and you know that if you do something with not, the invariants do not change, and that just reflected in the fact that generating series are the same. Why quivers? Why not just these Q series themselves?
well, we are in fact interested in this, maybe from physics viewpoint, but kind of categorified level, because this generating series that we obtain, they are supposed to count states in some Hilbert spaces that appear in the supersymmetric theories that we consider. So, like, this is general philosophy in all this physics approaches, that we have certain supersymmetric theory. There is some Hilbert space behind that, and often what we can compute explicitly are just the numbers of these BPS states, which then come in the form of this generating series. But we are interested in the structures of the spaces. So in that sense, we are not only interested
True,
in
but then you should rather look for, I don't know, some categories which somehow produce this related to this symmetric quivers. And from that perspective, it all looks two-dimensional. So, and since you mentioned 4D n equal 2, it's rather three-dimensional Calabi-Yau. Then it's a bit symmetric quivers. It's why you have generating series in commuting variables, because for symmetric quivers your Euler form is symmetric. So then quantum torus in DT theory, it's commutative. That's why you have just generating series and commuting variables. It looks two-dimensional, and you mentioned some theories which are definitely three-dimensional.
yes.
So it's also a bit confusing. You do not see non-symmetric quivers in your story.
No. So I mean, for us, this is indeed the surprising point, which I admit I cannot explain, hopefully yet very well, why we just see symmetric quivers. But this is well, this is just what we see. We don't need to consider other ones, because all this information that is, like, at least for those knots, which is of interest, turns out to come just from symmetric ones.
So it's a bit mysterious. All right, more questions? Well, if there are no more questions, there will be a second lecture of Piotr tomorrow at the same time.
The same link, just to make sure.
Excuse me?
The same link should I use?
Yeah, same link. Yeah, you can use the same link. Yeah, exactly. All right. Well, then,
Thank you very
thanks
much.
for the talk, and see you tomorrow.
Thank you.
Bye.